Welcome to Chemistry at Hanania High School. Today we'll be looking at our last couple of sections of Chapter 13 dealing with solids, changes of state, and phase diagrams. Now solids, unlike liquids and gases, are held together by much stronger intermolecular forces. So they're packed very tightly together, and therefore they do not flow. They really just vibrate around fixed points. They're in constant motion, but they're not getting anywhere. And because they're packed tightly together, they are incompressible. Now, that has consequences to properties of solids. One major one would be density. Generally, the solid form of substance is the most dense. They're typically about 10% more dense than liquids, and it makes sense if you think about it. They're packed tightly together, which decreases the volume that the same mass of particles in compared to a liquid, and therefore you're going to have a higher overall density. One major exception to that would be H2O. H2O is actually less dense in its solid form than its liquid form, which means ice floats. And that actually is a very, very important exception, because if across the world in any climate where it got cold and water would freeze, ice didn't float, then basically as the ice forms, it would sink to the bottom, and lakes and rivers and streams would freeze from the bottom up, meaning the aquatic life that exists in them would basically die. And if you disrupt the aquatic life over a huge portion of the world, that would completely disrupt the ecosystems on Earth. So it's a very important exception that ice floats. Now, most substances, I said, are crystalline. Well, what does it mean to be crystalline? Well, you have a very ordered arrangement of atoms, ions, and molecules. On the particle microscopic level, you're put together in very ordered patterns known as a crystal lattice. And if you are ordered on the microscopic level, that means you're going to be ordered on the macroscopic level as well. And not all crystalline solids have the same shape. That's because there's fundamentally different ways on the microscopic level they're put together. Now, that smallest part that gets repeated to give us our crystal shape is called the unit cell. And while we don't get into the unit cells and crystalline shapes, it's important to understand that if most solids are crystalline and ordered in nature, then on the macroscopic level, they're going to be crystalline and ordered in nature as well. Now, when you have two or more different molecular forms of the same element in the same state, you have what is known as allotropes. One common example of allotropes would be diamond and graphite. They're just two of the many different allotropes of carbon. They're two very common ones that most of us have seen. Now keep in mind, while graphite and diamond have very different physical properties and look different, they're fundamentally the exact same chemical, just bonded together in a slightly different way. In graphite, you have sheets of carbon that are bonded together with three other carbon atoms and loosely bonded in between. Whereas in diamond, you have three-dimensional bonding in every direction. Every carbon atom is strongly bonded to four other carbon atoms around it. And that gives diamond its very, very hard, rigid form. Now, I did say that most substances are crystalline. That doesn't mean that all substances are crystalline. There are some substances that are amorphous. Amorphous substances lack that internal ordered structure. And because of that, they don't have a definite melting point or freezing point. They melt over a range or gradually soften. So the pockets of uniformity that exist will basically require different temperatures to liquefy, and it slowly starts to liquefy in various regions throughout. And instead of one melting point, you have a gradual melting. So it seems like with glass, as you get it hotter, it becomes less solid-like and more liquid-like as it starts to flow a little bit. And get it liquid-like enough, get it hot enough, and it'll actually be in its liquid form. So where does it actually physically melt? Well, over a range of temperatures, not one specific temperature. So glass, rubber, and certain types of plastics are examples of amorphous substances. Now, the melting point of a substance is the temperature at which that solid turns into a liquid. And what's happening as the solid is heated, the molecules vibrate faster. They're gaining kinetic energy until those vibrations are strong enough to break apart the intermolecular forces that hold the solid together. The stronger the intermolecular forces, the higher the melting point is going to be of a substance. So melting point is a ranking of relative intermolecular forces for a solid. Now, some of the types of solids that have the highest melting points would be ionic compounds. And that's because that cation to anion three-dimensional bonding is a very strong electrostatic attraction. Much stronger than the relatively weaker forces that exist between molecular compounds. Now, besides melting, the transition from a solid to a liquid, if we keep heating a substance up, liquids will eventually change to a gas. The process of doing that is known as vaporization. So the process of liquid changing into a gas or vapor is vaporization. Evaporation is when you go from a liquid to a gas and you're below the substance's boiling point. So surface particles that are moving fast enough can overcome the intermolecular forces of the particles around them and escape and become a gas. So only particles moving fast enough to overcome those intermolecular forces have the energy to escape and become a gas. Now, when those high-speed particles leave, it drops the overall average kinetic energy of the substance. It takes energy for it to break away. So overall, evaporation is a cooling process, which is how our bodies use evaporation. When we excrete liquid on the surface of our skin through sweat, and that sweat evaporates away, it actually cools off the body. In order to become a gas, those particles need energy, and they're stealing that energy from us. So evaporation is a cooling process. Now, heating a liquid makes more high-speed particles, and the rate of evaporation is then going to slowly increase. So as we get a substance hotter and hotter and hotter, we have more and more high-speed particles. So we've got more particles on the surface of the liquid with enough kinetic energy to break away. Now, we still haven't talked about boiling yet. This is really still dealing with the concept of evaporation. Now, one thing that sometimes people think is, well, wait a second, if a glass of water is evaporating and that's cooling it off, how come the glass of water doesn't eventually freeze solid? Well, it's because it's sitting in a room, and as it is cooling off inside the room, which is a warmer temperature, immediately dumps kinetic energy back in, maintaining a constant higher temperature from the liquid. So while it is cooling as it's occurring, a liquid sitting in a room is going to be continuously warmed up by the room. Now, when you look at these diagrams, these are examples of what we call a Maxwell-Boltzmann distribution, which looks at the portion or part of or percentage of molecules at various kinetic energies. Now, the blue curve represents a colder temperature. I know it's a higher hill, but don't let that fool you. That's the lower temperature situation. And the red would be the higher temperature situation. So if you think about this purple line here being the energy needed to vaporize, how much kinetic energy do we need to break away? You can see that the cool liquid has significantly fewer particles with enough kinetic energy to break away. And as we increase the temperature of the liquids, we get a much greater number of particles that break away. And what's really happening here is around the peak of the hill, somewhere around there, that's where our average kinetic energy is going to be. And obviously a hotter substance should have a higher kinetic energy. So while it's a lower hill, the red particles have a higher average kinetic energy. Now, vapor pressure is what gets created when those escaping vapor particles push up on the outside world. So as liquids evaporate, those vaporized particles start to exert an upward pressure on the outside world. And increasing the temperature is going to increase the vapor pressure of a substance, because as we increase the temperature, we get more particles evaporating. And as we get more particles evaporating and colliding with the outside world, we get a higher vapor pressure. Now, different substances have different vapor pressures at any given temperature. Why is that? Well, it's because they have differences in intermolecular force. So the harder it is for you to break away, the lower your vapor pressure is going to be at any given temperature. So in this particular diagram, you can see that the ethanoic acid is creating the lowest vapor pressures at a given temperature. So that must mean it has stronger intermolecular forces than the other things around it. Now, boiling point is kind of the extreme of evaporation. Evaporation is a surface phenomenon, and yes, as it gets hotter, it starts to evaporate faster. But remember, as it's getting hotter and evaporating faster, its vapor pressure is starting to build. Well, the vapor pressure is what's putting up. Atmospheric pressure is the pressure that the air particles around the liquid is pushing down. And really, boiling isn't about a temperature as it is as much about those two pressures that are working against each other. When vapor pressure rises to equal atmospheric pressure, then that's when you get boiling. So unlike evaporation, boiling happens at a set temperature and is not limited to the surface. So at a given atmospheric pressure, what temperature do we need to get to make the vapor pressure equal the atmospheric pressure? Higher atmospheric pressures, harder to boil, higher boiling temperatures. So boiling point is not a specific temperature. The normal boiling point is what we think of as the boiling point of a substance. But technically, the normal boiling point is when you're at normal, typical 1 atm atmospheric pressure. What is your boiling point? So remember, boiling can happen at a variety of temperatures. Your normal boiling point for something like water would happen at one temperature. At 1 atm, water is going to boil at 100 degrees Celsius. And remember, the temperature of a liquid never gets above its boiling point, because as it's boiling, the boiling particles breaking away and becoming a gas are stealing kinetic energy, and that prevents the other molecules basically from rising in temperature. So as long as you have boiling occurring, which is taking away kinetic energy as it happens, you're not going to get any hotter than your boiling point. But once all of the particles have broken away, now your energy goes to not breaking the potential energy overcoming intermolecular forces, but it starts to increase the kinetic energies of the particles and they speed up again. So it really deals with when a substance is boiling, the potential energy that's being overcome is stealing all of our energy. And once the potential energy and all the particles have broken away, your particles are free to speed up again as we dump in more energy. And boiling points are definitely tied to the atmospheric pressure. When you're at sea level, you're at a very specific 1 atm or 101.3 kPa. Whereas if you go on top of Mount Everest, because your atmospheric pressure is significantly lower, about 1/3, then water boils at a significantly lower temperature. Because remember, it's when atmospheric pressure and rising vapor pressure equal. If atmospheric pressure is lower, then the atmosphere or the vapor pressure doesn't have to rise as high to boil. So consequently, on top of Mount Everest, yes, water will get to its boiling point more quickly, but it's going to be a lot colder, and it would take significantly longer to hard boil an egg in that colder water. Now, the next phase change, we talked about solid to liquid and liquid to gas, is sublimation. So changing from a solid directly to a gas is the process of sublimation. Now, some of you may know dry ice, solid CO2. It's called dry ice because, one, it looks like ice, but it doesn't melt and become a liquid. It goes straight from a solid to its gaseous state at atmospheric pressure, so it never looks like it gets wet or becomes a liquid, hence the name dry ice. So dry ice is an example of a substance that sublimates that some of you may have seen before. Leave it sitting on a table and it's going to slowly disappear without ever becoming a liquid. Now, other substances like regular ice also sublime, and that's really how frost-free refrigerators work. In the freezer of your refrigerator, as ice particles sublime and become a gas, if they stayed up in the upper freezer, then what would happen is they would eventually recondense on the side of the freezer. Liquid would then freeze back into a solid, and you'd see the ice slowly building on the sides of your freezer. Well, if you have a frost-free refrigerator, what happens is there's basically a fan that as the ice sublimates, if those gaseous particles are removed from the freezer, then they don't get a chance to refreeze. And you've seen this idea if you've been gone long enough. The ice cubes in your trays, or if you have an automatic ice maker like most of us do nowadays, over time those ice particles start to get slower. And a big negative is between the ice particles, as the ice itself is sublimating, those gases that come off often strike the particles around them directly connected to the ice that's sitting next to them, and then they refreeze. And what happens is there used to be a space between the two ice particles. Well, as some ice sublimates, becomes a gas, goes back to a liquid, and then refreezes, your ice particles start to freeze together. So in time, they become slightly smaller, but they freeze together to be a big ice chunk in your freezer. Now, if you look at the boiling point of a pure liquid, you would see that it would slowly increase in temperature until it starts to boil. And at the boiling point, its temperature would remain constant. And then after it boils, once again, it would start to increase in temperature again once everything has become a gas. Now, if you look at this boiling point diagram, you can see that at the beginning, or over time, it's increasing in temperature, and right around 82, 81, somewhere in there, we hit a plateau. Well, and then after a while, it starts to go up again, and then around 100, we hit a plateau again. Why does it do that? Well, that's because this was actually a mix between two different substances. So this would be what the boiling curve looks like of a blend of rubbing alcohol and water. Rubbing alcohol has a lower boiling point, so it's going to boil first. And remember, when it's boiling, the change in potential energy is taking all of our energy, so the temperature becomes constant. But once all of our rubbing alcohol is boiled away, now the remaining water molecules are going to heat up until they get to their boiling point. Now, going in the opposite direction, everything we looked at just a second ago, we had to put in energy to make all of those changes of state happen. Now we're going to look at the changes of state that release energy. In other words, we have to take energy out to make them happen. One good example that would be condensation, which is a gas or a vapor becoming a liquid. And really what's happening is slow-moving particles, as they're moving past each other in the gaseous state, start to exert attractive forces, because speed is one of the things that makes those gaseous particles have no intermolecular forces. It's not that they're are not there, it's just that based on the speed of the particles, they're negligible. And the kinetic energy overcomes those attractions and they just move right on their way. But if the particles are moving slow enough, they're not moving fast enough to basically ignore intermolecular forces, and they start to clump back together and become a liquid. And they'll do this in spots, which is why you'll see condensing on windows or mirrors. It starts out as tiny little spots, and those tiny little spots, once they form, start to quickly accumulate. And that's because after you have a little bit of that liquid there, then high-speed particles that bounce into the liquid and don't bounce off but get trapped end up accumulating in those drops, and those drops very quickly start to form. So unless you have your defrost on in the winter, very quickly your windshield can become impossible to see out of. Now another change of state that requires the removal of energy, we have to take energy out to change a gas back to a liquid, would be going from a gas to a solid. That's known as deposition. And this is kind of the opposite of sublimation. In deposition, like in the formation of snowflakes, you have gas particles that don't liquefy. They're going straight from the gas to the solid form in the upper atmosphere. And then when they get heavy and dense enough, then they start to fall. And then the final one we'll look at is our liquid to solid, which is our freezing point, which is probably the one we're most used to, because while we don't hit the boiling point of water outside, we do often in the middle of winter hit the freezing point of water. So it's the temperature at which a liquid goes back to a solid. And once again, we have to remove energy to freeze something. And that's why it's hot over by your refrigerator. In order to keep everything cold and to freeze the stuff that's in your freezer, you have to remove energy from the inside of the refrigerator and dump it into the room. So these are all changes of state that require taking energy out, or a release of energy. Now the fancy name for that is these are all exothermic physical processes. And the ones we looked at before that needed energy to occur, those would be endothermic processes. Now what happens to a liquid when we have a closed container? It's a little bit different than an open container. In an open container, it'll keep evaporating, and as the room keeps heating it up, it eventually will all disappear. Well, that's because when you become a gas and you leave, you're not going back to that liquid state. Well, close the container and those particles can't do that anymore. Now at the beginning, you're going to have a very high evaporation rate, but you're having almost no condensation. It would be very rare for those gaseous particles to come back into the liquid if there's no top on our container. So we start with a very high evaporation rate and a very, very small or negligible condensation rate. Well, over time, the evaporation rate's going to stay constant because it's in a room of constant temperature, so the liquid's going to stay at a constant temperature. But the condensation rate is going to slowly start to build if there's a lid on the container, because you're not letting the particles escape anymore. And as the number of gas particles increases, then the likelihood of a gas going back into the liquid increases as well. So your evaporation rate stays the same, and your constant condensation rate, the change from gas back to a liquid, slowly starts to increase. And eventually those two rates are going to become equal, and you have what's known as a dynamic equilibrium. Two things in equal and opposite rate from each other, and the particles then are being traded at the exact same rate. So you end up with no net change in the number of liquid particles and no net change in the number of gaseous particles once you reach that dynamic equilibrium. Now, a phase diagram is a diagram that shows the relationships between all of these different states in a closed container at different temperatures and pressures. So at what temperature and pressure do you have solids, liquids, and gases? Now this would be the phase diagram of water. And the phase diagram of water has kind of a unique characteristic to it. You'll notice the tilt here, this line between solid and liquid, doesn't tilt in this direction, it tilts in that direction. And that means as we pressurize the solid, we can actually change it to a liquid, because remember, a liquid was one of those rare things that was actually more dense as a solid than it was as a liquid. Now, one of the things you see on this diagram is all of the different transitions between gases and liquids. So this line would represent basically your different boiling points, the transitions between the solids and the liquid, so these would be your different freezing points. Notice boiling point changes significantly more than freezing point. It's not quite solid, but it's fair or constant, but it's fairly close to it. And then down here, these would be all of your different sublimation slash deposition points. So right there in the middle, you have a magic temperature and pressure where you can actually have all three states of matter coexisting. Normally at other temperatures and pressures, you can really only have two states of matter. Like in a glass of boiling water, you can have the liquid state and the gaseous state, but there's not going to be any ice in there with it. You only have two states of matter in equilibrium with each other. Well, at the triple point of the substance, this point right here for water, you can actually have all three states of matter existing together. And also substances have up here what's called a critical point. It's a temperature and pressure above which you're not going to be in the liquid state anymore. Now, if you look at water side by side with CO2, you can see water has this between its liquid and solid, but CO2 has that line. And that's pretty much what you're going to see with most everything else but water. Now, one of the things that's unique to CO2 is notice this is atmospheric pressure. The triple point of CO2 is the higher pressure than normal atmospheric pressure, which means at 1 atm, as you warm up the CO2, it goes straight from a solid to a gas without ever become a liquid. In order to have liquid CO2, we have to have it pressurized, get to a higher pressure. So the triple point was the temperature and pressure where all three states of matter coexist in equilibrium. It's not that you have solids, liquids, and gases together. It's you have solids, liquids, and gases in equilibrium with each other. Normally, at a given temperature and pressure, you can only have a couple of states of matter in equilibrium with each other. But at the triple point, you can actually have all three states coexisting. And then also, you saw in the diagrams, the critical point, above this temperature, the substance can only exist as a gas. Now, the last thing we want to briefly look at is plasmas, the fourth state of matter. It's a gaseous mixture of electrons and positive ions. If we keep dumping energy into a gas, the kinetic energy increases, but eventually we dump in enough energy that we start to knock out electrons from the gaseous atom. And you end up then with cations with electrons around them. So it's a gaseous mixture of electrons and positive ions. Now, this generally only occurs at very high temperatures where the kinetic energy is enough to strip electrons away from the gaseous atoms. But those gaseous atoms are positive in charge, the electrons are negative, so this is typically something that only exists for a small period of time because they will attract each other and go back to just a high energy gas. So plasmas aren't a normal state of matter that exists, but they do exist in everyday situations on a pinpoint or microscopic level when you spike very high temperatures. But in general, they're very unstable and only last for a brief moment in time. And yes, at lower temperatures in fluorescent light bulbs and neon signs and lightning, the aurora borealis, the northern lights, that's an example of a plasma. And the reason it shimmers is because it's forming and going back to a high-speed gas as you're watching. And that ends our Chapter 13 set of notes.